Alright, so this video is going to talk about section 14, and specifically we're going to go over a summary or in broad strokes outline of the main propositions or facts in section 14. So to remind ourselves, section 14 talks about Cartesian planes over an abstract or an arbitrary field. Okay? When you actually get into your models of geometry that are built off of Cartesian planes over some field, you'll have the exact field, but in general, when we talk about our Cartesian planes, you could insert pretty much any field you want into the mold. So to remind ourselves what a field is and what a Cartesian plane is, I'm going to go ahead here and swap us over to the handout for section 14. So this guy here is totally posted up on Canvas for you guys, and the first thing here is the field. We talked about this in a previous video. So to remind ourselves, a field is simply a set. It's got two operations, addition and multiplication. You can either use the X symbol for multiplication, the dot symbol for multiplication, or as many people do, they just put the two elements next to each other. In this setting, it doesn't matter which you do, unlike in linear algebra where dot product, cross product, and scalar product, all different things. Okay. Specifically, you need to have the set be closed under addition and multiplication, and you have the following conditions you have to worry about. Your set has to form an abelian group over addition, and your set also has to form an abelian group over both multiplication and addition. Only caveat here is you actually throw out the zero element when you're dealing with the abelian group over multiplication. Last thing is, when you have addition and multiplication, you do have your distributive laws in play here. Okay. So we talked about that previously in common examples. To remind ourselves, some of those common examples are set of all real numbers, set of all rationals, or your fractions. We also previously talked about the characteristic of a field, and one of the big conclusions that we talked about was, hey, characteristic 0, and the big thing here is, I really should say that's a big deal, because one of the things we're going to have in our propositions is that, hey, your field has to have characteristic 0. In other words, we'll be looking at these fields that are similar in acting, like real numbers, like rationals, or actually also Q adjoins some root, R adjoins some root, complex numbers, etc. Okay, so those are the standard sets of real numbers. I should say real numbers, fields that we'll get with characteristic 0. We also talked about Cartesian plane, and this guy here was simply ordered pairs. So you're looking at your XY coordinate system where the numbers that you're pulling from is pulling from some set field. And then we're ready to jump into our propositions, and all of the propositions are listed on the same handout, but I'm going to go ahead and put this where we can have pictures, etc. Okay. So we're going to be focusing right here on our results, our propositions. So the first proposition that we have is proposition 14.1, and proposition 14.1 says, pick any field you want, doesn't matter which one, then the Cartesian plane formed from that field, and remember here, Cartesian plane, the symbol was a capital letter pi. The subscript matches whatever the name of your field is. So here we used F for an arbitrary field, but if you actually have a named field, you go ahead and put that name down here. This guy here is going to satisfy the incidence axioms as well as the parallel axioms. In other words, what this tells you is that if you've got a Cartesian plane, you're looking at an affine plane. So I'm just going to walk through the outline of this guy. I'm not going to put it in a T-chart. I'm just going to outline it for us. So the first thing we've got is, and actually let me make this a little bit higher up. Excellent. So first thing we've got here is for the first incidence axiom, and remember our first incidence axiom said pick any 2 points in your geometry. You better be able to find the unique line that contains those 2 points. So here we have both the operations of addition and multiplication. Automatically our abelian field with respect to addition would give us negatives, so that's like saying subtraction. And a abelian group with respect to multiplication gives us inverses, and that's like dealing with division. Okay, so we have our normal operations then. So what we can say here is you take your two ordered pairs, Because remember, Cartesian plane is all the points are built from ordered pairs. So you take your two ordered pairs, and maybe it's as simple as x1, y1 for one of the ordered pairs, x2, y2 for the other ordered pair, and you can throw it into the standard formula right here to get your line. And if the two x values happen to be the same, you also have, so if you have x, y1, so maybe x1, y1, and the second one has the same x value, so maybe x1, y2, then in that case, the line corresponding to these 2 points would be a vertical line, so x equals whatever that x coordinate was. Okay, so that's the only case not taken care of by that sentence. So that says, or that tells us that the first incidence axiom is going to work out. Note, this guy totally works on horizontal lines just fine. You'll just get the slope right there as 0. Now, for the second incidence axiom, it says start off with some line and you'll be able to pick 2 points. So here, what do? Start off with some arbitrary line. Here, the only difference from what we've done in the past is the coefficients a, b, c, and also that 0 all have to come from your field. That's the only difference from what we've done previously. Now, since we always have the 0 and the 1 element in our field, that means we can always plug in x equals 0 and x equals 1 into our formula for a line and solve for the y values corresponding to x equals 0 and x equals 1. So if we actually did that, x equals 0, well, this would mean that in terms of scratch work, we would have by plus c equals 0. So y would equal negative c over b. And if we plugged in x equals 1, well, the scratch work would be, plug in x equals 1, we'd have a plus by plus c equals 0. So this would tell us that by equals, well, negative a minus c. So y would equal negative a minus c, and then you divide by b. So we'd have negative a minus c all over b. Okay. So those would be your 2 points. And notice they have to be 2 different points because the x coordinates are 2 different points. And we know that the second coordinate has to exist in the field because division and subtraction totally come from your addition and multiplication, so no worries there. Okay. You could have done the same thing with your y equals 0, y equals 1 as well. So that tells you the second incidence axiom holds. Now, the third incidence axiom tells us that we can have 3 points that are not always on the same line, or not all on the same line. Again, for sure, your field always has at least 2 elements, the 1 element and the 0 element. Or to be very formal, the additive identity and the multiplicative identity, which means you can always build the 3 points 0, 0, 1, 0, and 0, 1, and those guys will turn out to always be 3 different points. If we go ahead and graph this Cartesian plane, it would look like those 3 guys. Your origin and then 1 point on each of the x and the y axes. And so that tells us we're now in incidence geometry. The only thing left to do is Playfair's axiom. And Playfair's axiom says what? Well, it says given some line, given some point, you're going to be able to go ahead and find the line that is parallel to your given line through your given point. So this tells us that, hey, what would we do? Well, if the 2 lines are parallel, we know the slopes are the same, so copy down the same slope. And if you know you have to pass through the point AB, you're going to have here y minus b and x minus a, which gives you your line. The only time when this doesn't work is if you don't have a slope, so that would be vertical lines. So if you're dealing with a vertical line, and I'm going to tack the picture right up here at the top. So suppose you have some vertical line. Okay, so here's your line, maybe x equals, I don't know, how about c? We haven't used c. And then you have this point AB over here. Well, if you want the equation of the other vertical line, well, it's just going to be x equals a. Okay, so that would be the case for vertical lines. Please note if your point actually is on your line, the parallel line is simply the same line that you started with. Okay, but that'll automatically happen with this formula as well. You'll get that back. So that tells you that Playfair's axiom is satisfied because you're always able to build exactly one line that's parallel to your given line through your given point. So this tells us that all four of those axioms are satisfied, which means we actually have what the theorem says, and we in fact know that these Cartesian planes over a field are in fact affine planes. So some of you asked way back when in section 6, hey, we have some examples here of affine planes in finite geometries, but can it happen in infinite geometries? The answer is yes. Here's examples. So the little change here that you might not have noticed, not only was regular Playfair's axiom satisfied, but since there was exactly one line always, we in fact had the stronger version, and that's the affine plane thing I was telling you about a little bit ago. All right, so Proposition 14.2, not going to lie, Proposition 14.2 really feels like it has no point whatsoever, but it in fact is one of the key things for what we're going to do in Section 14, and the key main thing we're going to focus in on in Section 14 is dealing with configurations. Okay, so here's what this proposition says. It says you've got some Cartesian plane, you're over some field F, so the same thing we've been dealing with. It turns out it's always possible to do something called a linear change of variables. Okay, a linear change of variables says you start off with whatever x and y coordinates you have. You're now going to reassign all of these x and these y coordinates by some expression. So new x coordinate would be old x coordinate times something plus old y coordinate times something plus some constant. And it's okay that some of these guys are 0. It's okay if some of these guys are 1. If both b and c are 0 and a is 1, nothing changed for your x coordinates. Same deal with y. The linear is talking about that this expression right here is linear, so your x and your y are only raised to the first power, and you have all constants d, e, and f that you're dealing with. Okay. Now, what is this? Oh, and here's the extra caveat. Your new axes, so your new x and your y axes, can be any two intersecting lines, and your new unit points are any given points on those lines that are not equal to your intersection point. So the intersection point of your new line, that is going to correspond to your new origin. And just to remind ourselves, unit points, that's who you tag as 1, 0 or 0, 1. It's going to give you essentially like the scale, if you will. So if we actually had quote unquote units attached to all of the numbers on your x and your y axes, this would be like a change of units, like moving from inches to feet. That would be this type of deal. Now, that actually isn't where the word unit comes from. The word unit in algebra, and when I say algebra, I do not mean high school or college algebra. And when I say college algebra, I mean the class college algebra, not algebra in college. So like high school algebra, it's anyway, moving on. Unit actually comes from the number 1. Okay, so just like fields were defined as you do a certain thing, this unit here is a very, very technical term, and it in this case is referring to our number 1s right there. But in terms of being something that's not what it means mathematically, but totally is what's going on behind the scenes, you can think of this as changing like between inches to feet or between inches to centimeters. Okay, what happens? Your numbers scale out a little bit differently. Okay. Still the same points, they're just going to be tagged with slightly different numbers for your coordinates. Now, I should have a picture of what all this means. So here's how we're going to use this. Okay. So one of the things that we're going to be looking at is something called a configuration. A configuration is simply sum of the points and sum of the lines from your Cartesian plane over an arbitrary field. And one of the things that we'll be doing is checking to see if that particular configuration actually does exist or could exist in your Cartesian plane. So suppose you have this configuration right here, these points A through E. You've got, 4 lines that connect some of the different points together. Okay. So Proposition 14.2 says it's possible to make a linear change of variables where your new coordinate axes are any two intersecting lines, doesn't matter which. The origin is going to be the intersection point, and your new unit points are any points on those lines. Now, it is the best practice if you're dealing specifically with a configuration is to grab some of your longest lines to be tagged as your new x-axis and y-axis. I personally like to pick the longest lines that are towards the bottom of the configuration and towards the leftmost side of the configuration, just because it means once we do this linear change of variables, we're going to get a new configuration that's pretty much housed in the first quadrant of your xy coordinate plane or your Cartesian plane. Okay, you don't have to do that though. So starting off with this little example picture, this example configuration, what can we do? I'm going to go ahead and pick on these two lines. So those two lines are going to turn into my new x and y axis. I'm going to be strategic about this and have the line that contains points A, B, and C turn into the x-axis, and the line that is A, D, and E turn into the y-axis here. Then you've got the intersection point of those two lines, and remember, any Cartesian plane over a field is actually an incidence geometry. That tells us proposition 6.1 applies, so there's going to be exactly one point where those two lines intersect if they're intersecting lines. And remember, we were looking for intersecting lines. Okay, that means our point A here is going to turn into, after our change of variables, our new origin. Then you have to pick your unit points. You can pick either B or C as the unit point on the x-axis. You pick D or E as the unit point on the y-axis. You pick, and then all of the other coordinates of all of the other points in your Cartesian plane would adjust accordingly. Okay? So let's see how this would actually look. I got a picture. Okay. So in this particular case, if we go ahead and actually square it up, notice our guy that was going to turn into the x-axis, so ADE, I went ahead and squared it up so it looks like a vertical line. So here's our y-axis. The line that was ABC, I went ahead and kept it still horizontal because it started off as horizontal. And the extra things is I went ahead and labeled our origin at A, the intersection point, and I picked D and B as our two unit points just because they were the first ones out. You don't have to pick them that way. You can actually pick any point one on each of the two new axes. Just make sure it's not the origin. Okay. So this is something that we're going to do. Take whatever configuration you have and essentially square it up. Now, you can always change how this looks, or if you want, you can keep it in the sort of skewed picture here, but most people find it easier to go ahead and square it up. But personal preference. Okay, so that's what we're going to use this proposition for. And in fact, I would say that this proposition 14.2 is probably one of the most important propositions in this section in terms of what we're going to be doing. Okay. So, this just highlights. Pick the line ADE, turned it into ADE, we just squared it up. Okay. So, proposition 14.3 is the second to last proposition. And this proposition says, hey, there exists a configuration in your Cartesian plane over some field F of 4 points A, B, C, and D, such that this happens. So let's actually square this thing up for ourselves to give ourselves a little bit of a picture. Actually, I lie. Let's go ahead and pull in the rest of the proposition first, and then I'll go ahead and give the picture. That way it's easier to see. Okay. So if we go ahead and pull in the rest of this proposition, the rest of the proposition says this is only going to happen if your field has characteristic 2. Okay. So if we go ahead and look at AB, so we have here A, we have here B, we have here C, we have here D. So AB and CD are parallel. So if we're in an infinite Cartesian plane and infinite geometry, maybe they actually do look like railroad tracks. If we're in a finite situation, they just don't intersect. If we then look at AC and we look at BD, again, same deal. The lines containing AC and the lines containing BD need to be parallel. And AD and BC are also supposed to be parallel to each other. And it turns out that this happens exactly when the characteristic of your field is 2. Okay. Now, if you haven't looked at the information on finite fields, and specifically finite fields when you throw them into a Cartesian plane, this is going to make no sense to you right now. Just fast forward to the video at this point. If you have already looked at the finite fields, notice this is exactly what? It's a copy of the Cartesian plane over the field z mod 2. It's exactly the same thing. This is actually a copy of that finite field. And what did we have previously? We saw when we were looking at finite fields that the characteristic of z mod 2 actually equals 2. So if you have a copy of one of those finite fields, so one of those Cartesian fields over z mod, pick your favorite prime number, you could actually still have an infinite field potential. Probably not. You might still have an infinite Cartesian plane, but the way it's structured internally has got some quirks, and this is one of the cases where you can actually get down here to characteristic 2. Weird, crazy, perhaps stupid crazy, but this would be a way to sort of make sure that your infinite Cartesian plane or your Cartesian plane over an infinite field really does act like we expect it to act. So it'd be similar to if you had the Cartesian plane when you're dealing over real numbers or over rationals. Okay. We are not going to actually be using this proposition, I think, hardly at all, if at all. Okay. All right, so last main thing here, and here is dealing with a skew field. A skew field is actually, the word skew there means we almost have a field. There's only one thing that doesn't happen, and the one thing that doesn't happen is your multiplication doesn't have to be commutative. In other words, it's okay to get that AB doesn't equal BA. Okay, so that's what a skew field is. We're not going to be dealing with skew fields, again, hardly at all, if at all. So these two guys are sort of throwing in of, hey, heads up, this is what's going on. But the main focus in these first 3 propositions really is dealing with proposition 14.2. That's the main one that we're going to be dealing with.